Next Tuesday, it will be on sections 8.2 through 8.5. I will post the review this afternoon if you want to look at it. So it'll be integration by parts, trig integration, trig substitution, and partial fractions. I'm sure I can come up with at least 5 problems associated with that.
This page, the derivatives and integrals, I seem to have lost mine.
Okay, I can get you another copy. So the other 2 sections will cover either on the last test or the exam. So section 1, we were talking about sequences, and sequences were just a list of numbers, typically in some pattern. And the main thing that we talked about was what happens to the terms in the sequence as n, the counter in the sequence, goes to infinity. So the choices were it converges, which means that the limit goes to a particular value, or it diverges, which just means that the term gets larger and larger and larger, or to infinity. So now we're going to talk about series, which is really what we're interested in. But to know about series, you got to talk about sequences. So yeah. So what is this? I don't even. Let me see what I've got here. This is just to remind me what to do. Okay. So before we talk about infinite series, let's just talk about series in general. So you can have finite series and you can have an infinite series. And the way series are usually represented is you have a summation sign. So that means you're going to add the terms together. Remember, a sequence basically said the nth term of the sequence was something. So I'm going to go. Let me just go back one more step. So a sequence, what you would do is you would say a sub n is equal to, say, 1 over n squared, where n equals 1, 2, 3. And I guess you could have a finite sequence, you could have an infinite sequence, but normally they have an infinite number of terms. So when it comes to a series, what you're going to do is you're going to add the terms together. So this is a series. So you will see a series look like this. You'll sum the terms from n equals 1 to something. We call it capital N, where sometimes n equals infinity. Well, it can't really equal infinity, but So if you have a finite series, then you'd have a finite number of terms in the sum. If you have an infinite series, then you have an infinite number of terms, which you can't physically do, but you can take, if you know that an infinite series exactly equals a result, then you might say that the 10 terms of that series is sufficient to give you a good enough approximation to that quantity. So let's just look at this example over here. So if I look, instead of having a sequence, so what I would have here is I would have 1 over 1 squared, comma, 1 over 2 squared, comma, 1 over 3 squared, comma, or 1, comma, 1/4, comma, 1/9, comma, 1/16. And so that's how you do a sequence. Now, a series, let's say we have the summation from n equals 1 to 6 of 1 over n squared. Well, what that's going to be is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared, which is going to be equal to 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 136. Okay, and that's some number. I don't know what it is. I guess I could do it on my calculator. So this has an actual number. So 1 plus 1/4 plus 1/9 plus 1/16, that's a 16, plus 1/25 plus 1/36, and so I get a number 1.491. And let's see if I'm sure there's a fraction associated with this. Yeah, the exact rational number is 5,369 over 3,600. Okay. Okay, so when you do a series, you get, and you evaluate the series, you get a number. Or you get, if you took an infinite number of terms, you might either get a number or you might get infinity. So one of the big things about series is determining, one, if it converges or it diverges. And secondly, if it converges, can you predict what it converges to? What is the value it converges to? Because you can kind of see here it's 1.49 something. So you might guess maybe it's 1.5, right? You might think that if you keep adding smaller and smaller terms, that you'd end up with 1.5. And that may be the answer. It may not be. I don't know. But sometimes you can kind of guess, and sometimes you can actually, there's a few limited series where you can actually come up with the actual final answer, which we'll look at. So if you look, well, let's go to the next page. So if we took the same series and instead of going to 6 terms, if we went to infinite number of terms, what is that equal to? It's going to equal to some exact value, or it may not, or may be equal to infinity. So the questions we have about an infinite series is, does it converge or diverge? And where is that important? Well, back to, earlier I was saying that the infinite series that represents the cosine is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... Okay, so that's an example of an infinite series. Each term, this is the first term of the infinite series, second term, third term, fourth term. And if we came up with that, but then we found out that it didn't converge, it wouldn't be very useful to us. So if you can generate a series, you want to know whether that series mathematically actually converges for an infinite number of terms. And if I do if I do an infinite number of terms, I'm going to get the exact result. It turns out that, yes, it does converge. Now, sometimes it converges for a limited range of numbers. So that's another thing we'll look at later. Sometimes the series converges for some numbers, but not for other numbers. It turns out the cosine converges for all numbers. So I'm going to just do a little diversion here for a second, just to show you something, just to kind of give you previews of coming attractions. So if I take my graphing program and I put in cosine of x, I'll get that. Okay, and it repeats for infinity. So you think there's no way that you can come up with a series that is going to match that for any value of x. Maybe it works from -1 to +1, for a limited part of the domain. So let's just try. What I'm going to do is I'm going to add the different terms one at a time to the equation for the cosine. So the first term was 1. Okay, so let me plot that. So this blue curve exactly predicts the red curve at 0 and at pi, or is that right? Or is it negative pi over 2? Negative pi over 2, positive pi over 2. So it's perfect. It's a perfect correlation at a lot of points, but not every point. Okay. Then if you add the second term, which is minus x squared divided by 2 factorial, I think that works. Let's try it. Yeah. So that is 1 minus x squared over 2. So it's just a parabola. So now you can see the blue curve not only matches exactly here, but it starts to match the red curve close to x equals 0. So that's pretty good. So even two terms is pretty good approximation. Now we're going to add a third term, which is plus x to the fourth divided by 4 factorial. And now we have a fourth order polynomial. And you can see now that the blue curve predicts further away. I'm just going to keep adding the terms, and you can see every time I add a term, it's going to get me closer to, so let's plot that. So there we go. That's a sixth order polynomial. That's an eighth order polynomial. Is that another one? Minus x to the 10th, oops, x to the 10th divided by 10 factorial. And every time I add a new term, so I'll do one more and then I'll stop, x to the 12th over 12 factorial. So every time I add an additional term to that series, not only do I predict it better, closer to 0, but it goes out further. And so if I add an infinite number of terms to this sequence, if I have an infinite terms in this series, it'll predict out the cosine to infinity. It'll just add, it'll be, every time you add an additional term, not only will it be more accurate in the domain near 0, but it'll extend the accuracy out further and further. Because if you look at, if I zoom in to close to 0 and look at the two curves, you know, how far do I have to zoom in before I see a difference? I still haven't found any difference yet. Well, probably not going to because of the way. Okay, so with how many terms? 1, 2, 3, 4, 5, 6, 7 terms. You can't see any difference between the two curves, even at if I go out here and I start zooming in, you can start to see there is a slight difference between the two curves, but the error is not that much, and every time I add an additional term, that is going to get smaller. So let me do that, just show you one more term. I said it was the last one, but I lied. So if I put that next term in there, you'll notice they get closer again. So that's pretty cool, isn't it? Okay. Okay, so we got some theorems we got to go through. By the way, last night I was reading the paper. The couple that was the father and the daughter that was poisoned by the Russians, allegedly poisoned by the Russians with the nerve agent. They said what road it was on, and I thought, I'm going to see how close that is to where I'm staying when we go to Salisbury, and it's about a half a mile. Don't tell Martha. I haven't told her yet, but no, it's not unsafe, but it's pretty close. Okay, anyway, so we have this one. It's convergent and divergent series. It says for an infinite series from n equals 1 to infinity of a sub n, the nth partial sum is given by s sub n, where s sub n is defined as a plus a sub 1 plus a sub 2 plus dot 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 a sub n. So S sub n is the partial, you're adding the first n terms of the series. It says if the sequence of partial sums converges to some number s, then the series converges. Okay, so I'll explain what we'll use that. We'll use the example 1 over n squared, what they're saying. So they're saying, how do you determine if something converges? Well, you convert your series into a sequence of partial sums. And if that partial sum approaches some value s, then it converges. Okay. So let me demonstrate that, what they're saying here. So again, let's say that our series is 1 over n squared, which does converge. Okay, we'll find out why later. But if I make a table up of n, s sub n, actually not that, a sub n, and s sub n. So we'll start at n equals 1. So at n equals 1, a sub n is 1 over 1 squared. Okay, and at 2 you get 1 over 2 squared, and at 3 you get 1 over 3 squared, and so forth. 4 is 1 over 4 squared. That's 16 squared, 4 squared. Okay. So the partial sum here is 1. Here it's 1 plus 1/4. Here it's 1 plus 1/4 plus 1/9. Here it's 1 plus 1/4 plus 1/9 plus 1/16. So we get 1.25. I'm going to do it in decimal form. So the next one will be 1 plus 0.25 plus 1/9. And so that's 1.361. And the fourth term, we add another 1/16 to that. So that's 1.424. So that's the nth partial sum. Now if I went down, to infinity, the question is diverge or converge. So by looking at the convergence, so the actual sequence, so let me write that out, that's one. So a sequence is a set of numbers. So if I said what is the set of s sub n, it's equal to 1, 1.25, 1.361, 1.424, ... out an infinite number of terms. So these are the nth partial sum. And so for the series to converge, what you do is you look at the nth partial sum, and if that converges, then the series converges. Now that's, we're not going to worry about that we're not going to physically do that, but that's the official definition for how you determine the convergence or divergence of a series. I mean, another way, a non-mathematical way to think about it is if you have an infinite series where the nth term approaches some value, or not the nth term, but the nth partial sum approaches a fixed value, then it converges. If it doesn't, then it diverges. And it all depends upon how quickly these terms go to 0 if they're all positive. So in this case, I have my infinite series is this. There's another way. I'm going to give you two infinite series, one that converges, one that doesn't converge. And we'll find out why later, but right now I'm just going to give it as an example. So back in section 8 of chapter 8, when we looked at the integral, if we looked at the integral of 1 over x squared from 1 to infinity, we found out it converges to a certain number. We found out that the integral of 1 over x dx from 1 to infinity didn't converge. So in this case, it's not surprising that the infinite sum from n equals 1 to infinity 1 over n diverges. The reason the second one converges is because not only is the nth term getting smaller, but it's alternating between positive and negative, and so they tend to cancel each other out. So some series that wouldn't converge when they're all positive will converge when they alternate between positive and negative. And the example that I gave here is a case where it does alternate between positive and negative. So it's more likely if these were all pluses, it probably wouldn't converge, but it will converge if they alternate. Okay, so the limit of this, the limit S of these partial sums is, anyway, the limit is called the sum of the series. So if we take the limit, so we go back here, this last term here, when n goes to infinity, that's the value. So this would be the summation of a sub n from n equals 1 to infinity. The last term, which is really not a last term, but the term that it converges to in this sequence is the value of the series. It's the number. And if that number is infinite, then we say that the set of the sequence of the partial sums diverges. If that diverges, then the series converges. So if this converges, then the series converges. If the sequence of the partial sums diverges, then the series diverges. Okay, now here's a couple of series that you have probably seen before, and we're going to talk about them as far as convergence. So this is called a geometric series. You probably have dealt with geometric sequences before, where you have 1 over I guess what the example of 1 over x or n squared, that's an example of a geometric series where n is negative 2. So you've heard of, you remember arithmetic. Let me just go, this is a review question here. A little review of what you probably do know. Arithmetic sequence. So an arithmetic sequence would be something like 4, 7, 10, 13, 16, ... So you start at 4 and then you increase. There's a common difference, okay? And then you have the geometric sequence, and that looks something like, you could have, make sure I did this right, 3, 6, 12, 24, 48, ... Okay, so these are these listing of numbers. You start with 3 and each subsequent number is double the previous number. So that's an example of a geometric sequence. So a geometric series is the same kind of thing, except you add the terms together. And it has the form of some constant. In my example here, my constant is 3. And then you have the common ratio, which is the multiplying factor. And then you raise that to the nth power. So you have, in this case, 2 to the first power, 2 to the second power. No, that's 2 to the 0 power, 2 to the first power, 2 to the second power. So if I go back to my sequence, I can rewrite this. Instead of 3, 6, I can take, it's 3 times 2 to the 0 power, 3 times 2 to the first power, 3 times 2 to the second power, 3 times 2 to the third power, etc. Because that's 2 to the 0 is 1, so you get 3. 2 to the first is 2. 2 times 3 is 6. 2 squared is 4. 4 times 3 is 12. 2 to the third is 8. 8 times 3 is 24. So that's another way you can write this geometric sequence. And that's why you can write the geometric series in this form. It's, in this case, A is 3 and R is 2, the common ratio. Except A cannot equal 0. Then if you have that, then it doesn't work. So there's a convergence criteria for geometric series, and it says a geometric series with a ratio R diverges if the absolute value of the ratio is greater than or equal to 1. If the absolute value of the ratio is between 0 and 1, then the series converges. So that's one of 10 different convergence criteria, specifically for geometric series. And also, you can actually have an equation that tells you what that limit is. So it not only converges, but it converges to a specific value. So you have, in this case, you start from n equals 0. You go to infinity of a r to the n. The answer is a divided by 1 minus r. And I think, my example that I've been using, 1 over n squared, is an example of, no, it's not. It's, let me give you an example of one that converges and one that doesn't converge. So if I said the summation from n equals 0 to infinity of 3 times 1 over 2 to the n power. So that's an example of a geometric series. So if I wanted to show this, I would have 3, everything's multiplied by 3, so I'm just going to put that outside. And then you'll have 1/2 to the 0 power plus 1/2 to the first power plus 1/2 squared plus 1/2 cubed plus ... Okay. And so you'll have 3 times 1 plus 1/2 plus 1/4 plus 1/8. So the next one will be 1/16. And what it's saying is that we don't have to carry this calculation out. We have this rule that somebody's proven, and they've shown that if the ratio r is less than 1, which it is, between 0 and 1, then it's going to converge. And it's going to converge to this value. So if you looked at it, you'd say, well, let's just take an estimate of what we think is going to happen. You'd have 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Does anybody have any idea what that would converge to if you keep adding terms? 3 times 1 plus a lot of stuff. What do you think 1 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, if you keep adding those together, what do you think that might add up to be? 3/4, 7/8, 15/16. Well, yeah, 1 plus that. So this part adds up to 1. This adds up. So you add 1 and 1, you get 2. 2 times 3 is 6. So that should be the answer, just based on kind of intuition. And if we use the formula, what we would say is that the sum is actually equal to a, which is 3, divided by 1 minus 1/2. So you get 3 divided by 1/2, which is equal to 6, which is what we thought it would be. Just kind of guessing. But, this, if it was a third, then it would be, we could still use the formula. If you had a third to the 0 power plus the third to the first power plus the third squared, etc., etc., etc. So now, a case of where it diverges is if I had the infinite series n equals 0 to infinity of, say, 4 times 4/3 to the nth power. So that's another example of a geometric series, but the ratio, the common ratio, is greater than 1, and so the rule says that it diverges. And you can kind of tell why it diverges, because if you take any number greater than 1 and you keep multiplying it by itself, it's ultimately going to become a very big number, even though it starts out at a small number. If I take 4/3 to the millionth power, let's see what we get. Well, let's not use million because it might be over. Just trying 4/3 to the 10,000th power. Choose a big number. So I'll put that in my calculator. 4 divided by 3 to the 10,000th power. And it's more than the calculator can handle. So let's try something smaller. How about to the 100th power? So even 4/3 to the 100th power is 3.12 times 10 to the 12th. So it doesn't, I don't have to go anywhere near infinity to make this term, even the 100th term of this series is going to be huge. And so the 101st term is going to be huger, even bigger. Okay, so that's one of the convergence criteria. It's actually the only one that will allow us to predict what the answer is, unfortunately. The other ones just tell us whether it converges or diverges. Okay, now we have some rules that are kind of like integral rules, except we're using summation. And that's really the only difference here between integrating and series is series we add stuff together. Whereas integrals, we added it together too, but we made, well, in integration what we did is we added an infinite number of little rectangles together to get the exact answer. In a series, we add an infinite number of terms together to get an answer. So it's, and so the rules that we had for integrals, you kind of see similarities. This is like the integral of a constant times some function is equal to the constant times the integral of the function. So that's the same thing here. If you have a constant times some series, you can basically take the constant outside the summation sign and then evaluate just the summation of a sub n. So even though they don't show the intermediate step here, they is being, because I copied it from the book, another way of thinking of this is the same as c times the summation from n equals 1 to infinity of a sub n. So constants don't affect the convergence for one thing, and also it's just a constant multiplying factor. And then if you have a series that consists of two terms, each a function of n, then if you find the value for the series for this part, which is a, and you find this one separately for b sub n is b, then you just add them together. So adding two things together doesn't change the result. You can do them individually. It's like the integral of f of x plus g of x equals the integral of f of x plus the integral of g of x dx, of course. And if they're subtracted, you can just subtract them. So those are the three rules there. They seem pretty obvious if you think about them relative to integrals. Okay. Let me scroll down here. Give you a chance to write those down if you want to. Okay. Now the first and most important convergence test is the one that's shown here. You're able to eliminate a lot of series immediately without doing any more complicated analysis by using what's called the nth term test for divergence. And what it says is that the limit of the nth term of a convergence, so actually it's that's not really a sentence. It's just kind of a rewording of what we have. So it says if the nth term, well, it says that the actually, let me read that again, because if the summation converges, then yeah, it's kind of an opposite way of thinking of this. It says that if a infinite series converges, then the limit of the nth term has to go to 0. Now, it's another way of stating that, kind of in the negative version of it is, let me finish this. So one thing you can say is if the limit of a sub n as n approaches infinity does not equal 0, then the series diverges. And that kind of makes sense. If the terms don't get smaller, and they don't get smaller to the limit of 0, then there's no way that the series can converge, because you're going to continue to keep adding stuff on there. And if they're bigger, if they don't go to 0, then they can't fade out and disappear as far as the thing. Mr. Graham, did you have a...
Oh, I didn't mean to interrupt. I'm sorry.
That's okay. I'm at a good point if you want to...
Okay. I just want to make sure that everybody knows that they need to come to tutoring after.
Yeah. Hannah's leaving because she's going to New Jersey. You know about her.
I'll catch her.
Yeah.
Is everybody here today?
Let me see. Evan's not here. He's taking an SOL. But everybody else is here. Yeah, so don't skip out on study session.
I have another question. Did anybody bring you an Easter basket?
Me an Easter basket? No. No.
Talk to them about strategy, aren't I?
They know that I'm incorruptible.
Yeah, but it's always worth a try.
Yeah, that's right. Yeah, it doesn't work. Bribery does not work with me. I can afford my own chocolate. I just have to do it when Martha's not around. No, just kidding. No, actually, I have a drawer of chocolate, so it's okay. My Aldi's chocolate. So, for example, let's say we have a there's a third way of doing this. If the limit as n approaches infinity of a sub n equals 0, how do I want to say this? I know what I say. Convergence is not guaranteed. So here's a couple of examples. One, if I said that you have a series that looks like this, an infinite series, and it is n over n plus 1. And then I've got a series that is 1 over n, and I've got a series that's 1 over n squared. So if we look at the question, so I'm going to make a column here. Does the limit of a sub n as n approaches infinity equal 0? Does it converge? Question mark. So the answer to the first one is no. Okay, because it equals 1. You can see that as n gets very large, the 1 in the denominator becomes insignificant, And so you get n over n, essentially, which would be 1. So the first one, the limit does not equal 0, and does it converge? No. Okay. Does the second one, does the limit of 1 over n as n approaches infinity equal 0? And the answer is yes. Does it converge? No. Does the limit of 1 over n squared approach 0 when n goes to infinity? Yes. Does the series converge? Yes. So looking at the various descriptions, if the summation converges, then the limit equals 0. The limit of a sub n as n goes to infinity equals 0. So let's see that. If the series converges, yes. The limit approaches 0, yes. Okay. The second one is if the limit is of a sub n, if it doesn't equal 0, then the series diverges. So this is this case. No. Does the series converge? No, it diverges. If the limit of a sub n equals 0 as n goes to infinity, convergence is not guaranteed. So here's a case. The limit of a sub n as n goes to infinity does go to 0, but it doesn't converge. So you can only kind of use it in this direction. If it converges, then the limit goes to 0. So it allows you to eliminate this one, basically. Because this doesn't go to 0, then we know it diverges. But because it goes to 0 doesn't mean that it converges. Sometimes it does, sometimes it doesn't. So it eliminates anything that a lot of the series without having to go any further. Actually, that leads to this one. So I've already said that. If the limit as n goes to infinity of a sub n does not equal 0, then the infinite series diverges. So that really actually is I think this is I can't remember if the book does both of them or I made up the other one just to kind of prove that you have to be careful that you don't overuse it. Okay, so let's look at some problems associated with this. The first one is just find the first 5 terms of the sequence of partial sums. So they'll give you either a written out series or they will give you an equation. And what you'll do is you'll just make up, you don't have to make up a table, but it's probably easier to do that. And so what we'll do is we'll say this is when n equals 1 and this is n equals 2. You could start with 0 if you wanted to. We don't know what the equation is, so we can. So here are the first 5 terms. So what we can say is a sub n is 1, a third, a fifth, a seventh, a ninth, and the nth partial sum is going to be 1, 1 and a third. You can use your calculators for this. So we'll put it in fractions though. 1 plus a third. So I'll do it as an improper fraction, 4 thirds. Here we'd have 1 plus a third plus a fifth. So plus a fifth. Change that to a fraction. And we get 23 over 15. And then we add a seventh. And we change that to a fraction. And you get 176 over 105. And then you do the last one. So what we're doing is we're just adding these together. Then we add a ninth to that. Plus 1/9. Change that to a fraction. We get 563 over 315. Okay. So these are the nth partial sums. First partial sum, second partial sum, etc. The question is, does this approach some number? If this approaches a specific value, then the series converges. If it doesn't, then it diverges. Series diverges. Okay, so that's one. Verify that the infinite series diverges. So this, we only have 2 rules so far. We have we have the geometric rule for geometric series, and we have the nth term. And you could use either one of these. You could use either one of those theorems to prove that this diverges. So if you look at using the geometric series, well, how we would say is we would say based upon the convergence criteria for a geometric series, since R equals 4/3 and R is greater than or equal to 1, the series diverges. So if you go back to the rule here, now you're not going to have to memorize these. There's a table in the book, which I'll probably hand out next time, that gives you all the tests and all the criteria. You just have to know how to apply it. But if we go back to this rule here, so this is the rule. It says a geometric series with the ratio R diverges if the absolute value of R is greater than or equal to 1. So I'm using that criterion, and it works because it is a geometric series. If it was something that wasn't a geometric series, I can't use that rule. So that would be one way. Or you could say that the limit of a sub n as n approaches infinity does not equal 0, because you're going to have 4/3 to the infinite power, basically, which is infinity, and which is not 0. So since the limit of the nth term of the series as n goes to infinity does not equal 0, the series diverges according to the nth term test. So that's kind of a taste of things to come. You're like, oh God, this killed me. Okay. Now this one is not a geometric series, so the only other one we have is the nth term, and we've already looked at that as a previous example. But what you would do here is you would say, well, the limit of a sub n, which is n over n plus 1, does not equal 0 as n approaches infinity, therefore it diverges. So it would be basically the same. I could just copy the wording from the previous problem and just paste it over there, except it's not. So you could say since the limit of a sub n as n approaches infinity does not equal 0, and that's because I'm just going to make this up. That's not mathematically accurate, but I think you know what I mean. Okay, the nth term approaches 1, and now I'm going to copy it because I'm lazy. So. There we go. Okay, so that's kind of. Now the next one is that doesn't look like a geometric series. Oh, I know. I haven't talked. That reminds me, I haven't talked about. There is one other thing in this section, and it's called a telescoping series. So let me mention that. Looks like it's about time to quit, but let me just mention telescoping series. So let's look at. I'll show you why this comes out. If you take the denominator of this expression and you factor it, you'll have n plus 1, n minus 1. So we'll use this as an example of a telescoping series, and I guess you have to start from 0. So if you factor the denominator, and you have two terms, one that's plus something and one that's minus something involving n. And if I do a table, so this is n, and this would be a sub n, and we start at 2, sorry. What you would have is 1 over 2 plus 1 times 2 minus 1. Actually, that's not completely, well, you have to do one more thing, sorry. Yeah. We can use partial frac. We're going to rewrite this, and we'll do this tomorrow, but what we're going to do is we're going to write this as 1 over, I think it's like 1/2 of 1 over n plus 1. Don't write this down. I'm giving the general form. I'll correct it tomorrow. But if you use partial fractions, you have a term, and this that must be negative. So you have kind of like a positive thing, and you have a positive part and a negative part. And what happens with telescoping series is that in subsequent terms, the positive part cancels out the negative part, and all the intermediate things get canceled out, and all you're left with is the first part of the first term and the last part of the last term, and all the other ones cancel out. That's why it's called telescoping, because it's like you're taking the whole thing and going and folding in all the ones that you cancel out. But I need to spend more time talking about that, so we'll just stop there for right now. I will go ahead and let me give you a homework assignment for this section if you want to have something to do during study session, right? I guess I gave you an assignment on Tuesday, but I'm not sure where you were.
Have you decided yet what extra credits are going to affect our test twos, right?
Let me talk to you about that after class, but because I know why you're asking. But I have not yet, but I'm going to try to grade the physics extra, the 2 take-homes before tomorrow afternoon. I haven't looked at the other ones, but I haven't figured out the numerical numbers yet, and I haven't actually even looked at them, but I need to. So.